If someone were to ask you what the imaginary number is, you might answer j equals square root of minus 1. But do you actually know what that really means?
This equation raises more questions than it answers.
So let's begin with the basics, with the simple quadratic function. Now the values of x for which a polynomial expression becomes 0 are called the roots of the equation.
Yeah, in this case, they're the square roots of 2.
Right. Now let's shift this function here.
Now 0 is the root.
Exactly. So what happens when we move this function further upwards?
The roots don't exist anymore.
They do.
Where? They obviously don't lie on the real line, so they aren't real. So what are they? Imaginary.
Yeah. Square root of minus 1 is the imaginary number j, remember?
Oh.
I think things just got really complex. Now, no matter what a is, we can find the square roots in what is called the complex space.
What does this complex space even look like?
So let's construct the space. We can find the roots from the real line until this point. So the complex space contains the entire real line. Let's now take a value of 1 on this real line and rotate it counterclockwise by 90 degrees. We end up meeting someone, our imaginary friend J.
Oh,
This line is the imaginary line, and this is our complex plane.
wait a minute. You said j equals square root of minus 1. How can we get square root of minus 1 if we rotate 1 by 90 degrees?
Interesting, right? It's because of what this multiplication means on the complex plane. A rotation.
Multiplication could mean a rotation?
Yep. In terms of rotations, we can say that minus 1 or j squared is a 180 degree rotation of 1.
Yeah.
Now this equation indicates that two consecutive identical rotations take 1 to minus 1. This means that a 90 degree rotation of 1 corresponds to j, or the square root of minus 1.
Oh, yeah.
With the complex number system, it finally became possible to find the square roots of any real number, and in general, the n roots of a polynomial of degree n. So the imaginary number j, or the concept of square root of minus 1, which seemed very weird and confusing at the first look, turned out to be an idea of rotation in the complex plane.
Interesting.
Now, the complex plane offers a convenient and powerful way to express such rotations. A rotation of 90 degrees or pi by 2 radians can be expressed like this.
Oh, where did this exponential function come from? And why is j showing up both on the left hand side and as an exponent on the right hand side?
That's what we'll discover in the next episode. But for now, let me leave you with a question. You know how we always take two perpendicular vectors to represent any point on a 2D plane? Now, tell me, why do we choose the two vectors to be perpendicular? I mean, can you represent all points on a 2D plane if the two vectors aren't orthogonal to each other? Under what choices of the two vectors does it become impossible to represent every point on the 2D plane? Think about it. So yeah, meet you in the next episode.